Okay, so now let's try to describe this one-dimensional or two-dimensional random walk. So I'm gonna start with the random walk. Uh, random walk. So first of all, so how we can talk about this random displacement as a, let's say, so this. So any time with constant displacement with different length. So let's say like this. So after nth step from 0 to n, this is a resultant vector, displacement vector. So let's see, as a, we want to have applying these rules of random walk. So what we want to find out is here, like nth steps of displacement would be from the previous step. So that's n minus first steps of displacement plus, let's have this a one step vector as a L. So this L should be kind of random. Okay, and the length of this vector should be L as a constant or length of each step. Of course, tau is time interval. Just make it easy, let's assume tau is the same. So then from this, let's square of this equation, then what would be, so this is scalar value of Rn displacement square would be this vector dot product, or a plus b squared is a squared plus 2ab plus b squared, such that we can have Rn minus 1 square plus L square plus 2ab to Rn minus 1 vector dot product L vector. So now we want to have the average of root mean square. So mean of this square. So that is, let's apply for mean as I put as a bracket, which is an average mean. And that's what's important here is this here, the direction. This is a random direction. So by mean averaging out this random direction, actually the dot product turn out to be 0. So what that means is this R square will be like this term and this term will remain, while this term will go to 0 after mean value. So that is Rn minus 1 square plus L square is a constant. So this is just length L square and the plus 0. So then we can see that this nth will be described by n minus first. So we can come down as eventually, so this will become Rn minus 2 square average plus another L square plus 2. So we can see in the end, Rn minus 2 square plus 2 L square, and you can see the rule over here, something you can realize. We can go further and further. It will be eventually n times L square. So that's what you will be finding out. And this n is total number of steps. Total number of steps. And so eventually the time of duration, t, the time t can be described by the n times step times 1 step time. So with this, we can see, we can describe the n as a t over tau. So this will be L square of tau over tau times t because of this. All right, so what do we learn from here is basically, so the mean square will be described as L square, length scale over tau times t. So that we will define as this L square over t as a 2D by defining diffusion constant and t for one dimensional, and where we define d as a diffusion constant. I'll explain why we introduced 2 over here, and also the unit of the diffusion constant will be centimeter square over second, and typically that's how we will use it. Okay, so now we discuss about one-dimensional random walk. So I want to share with the 2- and 3-dimensional random walk results, which is computer simulation results. So you can see from left side, 2-dimensional, which means in X and Y. So this is an example starting from the origin and then over time, how this particle will move around the trajectories. And this right side is a 3D, so having X, Y, Z axis, and you can see very interesting pattern. So this is not an experiment, but it's a computer simulation results based on those assumptions we just discussed. So what we learned from here, the particle tends to explore a given region of space rather thoroughly. You can see this, and it tends to return to the same point many times before finally wandering away, meaning that the particle come here, and this is multiple times coming, this is multiple times coming. And sometimes it can go out of a new region. So chooses new regions to explore kind of blindly. It tracks and does not fill up the whole space of very uniform pattern. And that's in this simulation duration, but over a long time, I think it'll uniformly fill up those spaces. So in addition to those rules 1, 2, 3 for random walks, we assume that motions in X, Y, Z are statistically independent, which is holds in majority of the time if the space is not constrained. Then what we see is in average displacement of X, described as a root mean square of X, turn out to be 2 times d times time this diffusion constant and square root. Then likewise, Y displacement will be the same. RMS of Z will be the same. So in 2-dimensional case, the square of the distance from the origin to the point would be R square will be X square plus Y square. So if we have the RMS value of this, then it will be 2 dt plus 2 dt, resulting in 4 dt in 2D. And likewise, in 3 dimensions, it will be, instead of 2, 4, it will be, yes, 6 in 3 dimensions. So we will see this. The most important part is this square of displacement will be proportional to t time, means that we are interested in the spread. The dimension of distance will be now proportional to not proportion t, but square root of t. This means to explore further and further, it will be more, time takes more, like square of the time will be required. So that's the property of the diffusion phenomenon. So it will be depending on the distance. When the distance is narrowed down small, it can be very fast, but longer distance, it will take more time, more difficult, or less effective. for the particle to move around by simple diffusion. Okay, so thank you for your attention, and we will discuss next time a little bit more macroscopic aspects of diffusion, which is represented as a fixed law.